For those familiar with large language models, that's called prompting. So Albert gave the scene, and I now have to adapt my slides to this intro, which I will try to do. I think the scene is already set. We are in a fast evolving AI theater, and it seems like every 5 years we have a very, very fundamental, game-changing revolution, starting in 2012 with ImageNet moment. Those who lived through the ImageNet moment, they basically telling me that in the hall where this presentation was given back by Alex in 2012, the whole room knew that this is now a new era. And the same happened with Transformer 5 years later, which were not so much recognized in 2017, but much recognized 3 years later, when it was really obvious that everything is Transformers nowadays, and they scale and they do what it needs to be done to make AI really deep. And I think the third revolution are the large language models, and I experienced those myself during my time at Microsoft. I think it kicked really in with OpenAI, and I think that this is just the beginning of a new revolution, and we will see the next revolution hopefully sooner than 5 years, but definitely something big is coming, and this Europe should be prepared. So we heard large language models so many times. Large language models are the forefront of something which is called generative AI, generating content. Generating text is very simple because we just have to generate the next word, but we can also now generate images, generate videos, and who knows what is coming next. There is one thing in this whole mess of black box AI, and this is the scaling laws. Scaling laws really tell us how models behave when we give them more data and when we give them more parameters. That's what makes them predictable, and that allows companies to train those models at scale. And we are in a new era. I think this era started 2-3 years ago in the era of foundation models. We only know foundation models mostly because we have ChatGPT, we have Gemini, and we have these models which respond to text. But there is a lot of other things going on. What is a foundation model? Foundation model is a model trained on a huge amount of data and then fine-tuned to specific application. Very famous foundation models are, for example, Segment Anything from Facebook, or nowadays Meta. A very, very successful and super applicable model which segments, as the name says, any image you give it into different components. This can be used for very different applications in computer vision and so on and so forth. I think everyone knows the next one in the middle, protein folding, AlphaFold by DeepMind. I give a bet here in the room. This will be the first AI Nobel Prize. You can think of me when this happens, and otherwise, not. And then the third one, as an example, is Aurora. This is the first AI model which basically replaces numerical weather simulation at scale. I have a personal very deep connection to Aurora since I was leading this project for a couple of months, and this is where my great passion to simulation is starting. And we will see many more of those, and actually already see many more of those. So this brings us to NXAI, where we have these two branches, xLSTM, which I will mostly talk about as our language model, as our way of doing language models, and simulations, which is connected to language, but in a very distinct but very interesting fashion. So why are we setting up this NXAI, as Albert said it so to the point? We have this current situation that our models are trained on US, sometimes Chinese data, with Chinese and US moral and ethics, and we really don't know how to train these huge models. And when I say we really don't know, we are currently hiring people, and if you hire people and ask them, have you ever trained a large model? The first question is, what is large? And I say, well, a couple of hundred GPUs, no. And this is different in the US. People in the US, they have access to GPUs, they have a growing investment in, just put here the private equity in venture capitals, is just different. There are many of these opportunities to train large models, and this is something we really miss in Europe. And if we don't know how to train these models, we also don't know how to fine-tune them, how to align them, how to basically change them, how to make them safe and whatnot. So I think people have realized now that we need to be able to train those models in Europe. But there is something beyond large language models, and that these models are on the brink of changing the way we do things. And that is not only language, that is many other tasks. So if we, many different areas, want to run this disruption, we have to do that from inside, and otherwise we would just be overrun from outside. And now we come closer to large language models, which I have mentioned so many times. What is a large language model? It's a term which is not really defined. There's this discussion: was the former LSTM the first large language model or not? If you look up, probably the best definition is just it's neural networks really on steroids with billion of parameters. I think billion of parameters is the scale we are in. And those models are trained on a huge corpus of unlabeled text. Unlabeled means that basically those models are pre-trained in a fashion that they just predict the next word. It's very funny that we get our very powerful AI models which are changing the world by building machines which predict the next word. But actually that's what it is. And that's what works best and what makes them understand language, what makes them scalable, and what makes them applicable to many different downstream applications. And very interesting also for me is that this works across languages. I mean, people always say that it's very hard to train models on different applications, and I say, well, we can train them on Korean and I don't know, Indonesian dialects, and if you combine them, the models get more out of it. So there is something in this. They understand just more than we do, or they ignore the facts which makes these languages distinctable. So these models capture syntax and semantics of human language, and they start to build some general knowledge about the world. What these models do a lot is memorize. And I think the most popular large language models are so-called pre-trained transformers, generative because they generate the next sentence. If you abbreviate generative pre-trained transformers, you are a GPT, which I think everyone is familiar with, and they generate text by just iteratively predicting the next word, and again the next word, and again the next word, and using the next prediction already as input for generating the next word. There is a lot of knowledge nowadays in prompting. So prompt is what sets the context. Prompt is what gives we the language, we as a user, the language model as input. And this prompting is basically telling the model how to work. There is a lot of two other things which are important: alignment. There's a lot of discussion of how to align these models to our interests, to our way of doing conversation, to our values. This is what I said, that we need to understand how to train these models. We need to understand which data these models are trained for, because otherwise we will never be able to align them. And there is fine-tuning, so we can fine-tune them in language models to human feedbacks, in other areas to different dialects, different languages, and so on and so forth. We all know this history of transformers. I think the real big thing was GPT-3. That was the first language model which evoked interest. It was really showing this capabilities of doing translation at scale. ChatGPT was then taking the world with storm. I remember when ChatGPT came out at the NeurIPS, the biggest AI conference, 2022, suddenly everyone was sitting there and typing things into this box. I, of course, didn't know what was going on. I didn't even have my laptop with me. But the overwhelming excitement in the eyes of people just made me realize, okay, I have to try that out too. And that I think from there on, the path was just uphill. And the latest one is GPT-4, and there's a lot of different products now on the market from all tech giants, basically. What people usually don't know is that transformers replaced something which is called LSTM, long short-term memory. And people often ask, what is the difference between a transformer and LSTM? I would say they are fundamentally different. A transformer is reading a book by looking at all words together connecting all words with each other, and then giving you a statement of the book. An LSTM, it reads a book like a human. It starts at the first word, processes the whole book, building up a semantic concept, and then giving you a summary at the end. It's a very different ways of doing text understanding, very different ways of building such architecture. The one is so to say autoregressive because it runs through the whole text, generally looking at the different tokens. The other one is looking at all these tokens at once. And of course, this looking at all these tokens at once was a very new paradigm, and it appeared to be very scalable. Suddenly people were able to build larger architectures to make things parallelizable and so on and so forth. And this is the reason why these transformers really took off and replaced LSTMs at scale. And it made a lot of sense. LSTMs have two major disadvantages. So since they read a book like a human, they cannot revise a storage decision, meaning it becomes a very important character suddenly. The LSTM cannot basically vote down the decisions it made in the past and tell, okay, this is now something very important, I should probably put more weight on this decision, because it doesn't know what happens in future. It cannot combine these different contexts. The transformer can do that because it sees everything at once, and therefore it can weigh up and weigh down different connections. The second thing is LSTM have very limited storage capacities because, well, in the days when LSTM was founded, was invented, well, the main goal was to analyze a stream of bytes, bits, and a stream of letters, so there was not so much about storage. And LSTM is not parallelizable. Nevertheless, LSTM has very big success stories since it was invented here in Munich by Sepp Hochheit and Jürgen Schmidhuber. It started to win the first handwriting contests. It was the first translation tool in all, basically, speech recognition system, be it Android, be it Amazon Alexa, and Siri from Apple. But it was, you know, that the story ends in 2017, exactly the year. But also transformers have disadvantages. Since they look at each word together, each combination of words, they are quadratic in the context length. And think of giving transformer a really big book to read, it's very hard. Because, well, it has to look at all combination of different words. And that makes it very compute and memory intensive. And it only computes pairwise interaction, so each word with each other, with other words. And that makes it not very suited for semantic understanding, because in semantic understanding you need to build up a context. And if you think of yourself and when you have a conversation and you explain or you tell what happened in your recent holidays, and suddenly you get interrupted. And then you had something which you were telling, but you don't know exactly what was it, and you just need a small hint, and then you, yeah, this is it. I was telling a story. I was telling about this bar and this cocktail and whatnot. And this is the semantic understanding. You build the semantic understanding, and that's exactly what the LSTM is doing. So a transformer cannot build this concept because it only builds pairwise interaction. And that is also abstraction. Transformer cannot have abstraction. So we have these two different ways of modeling language, and the very, very naive question is, okay, what happens now if we take this old LSTM idea, but if we make it possible to put this LSTM into large architectures, if we make it parallelizable, so that we can train it also by feeding it the whole book at once, we give it a larger memory, that it can remember things better, and we make it give it the capability to revise this decision, so that suddenly decisions which are important in the future, which are more important than a decision in the past, it's very highly upgraded. And this combination of things make LSTM very, very powerful. Of course, you have to know what's the limitation of LSTM, and you have to know why LSTMs were replaced in the first place. Well, I mean, that's easy if you have Sepp Hochheit as basically as leading of this project, who was thinking day and night for many, many years why transformers outplaced these LSTMs. And the idea is, so that's the frame, so to say, and then we built these things, and then we were really scaling up, because it's all about scaling up, how far can you get. It's very nice to have a concept which proves practically in small examples, but you really have to prove it at scale. Prove it with the languages at these large models which are comparable. And now a slide full of formulas. You don't have to look at those formulas. I just want to say one thing. That is actually what, on the very left, the first formula is what I explained the whole time. So the C at the left is, so to say, the understanding of page 44, and the CT-1 is the understanding of page 43. So what the model is doing, it adds information. That is the E and the Z. So that's the information the model adds. It controls how much information is added. That is the LSTM idea. And you can use the same idea now with a much bigger context. So you look at the first formula on the right. Now we have a capital C, big C. That means there's much more context to store, much more context to add, but the same control mechanism and so on and so forth. So basically it's really transforming this LSTM idea now back to the future, to big architectures, to big data sets, to big GPU usage and so on and so forth. And what happens is that we get a very performant architecture. I show two plots here. We start with the left one, which gets us all super excited. That is something which is called out of context generalization. So what is happening here, we train our model to predict the next word, and the input is always a sequence of 2,000 tokens, 2,000 words, and it predicts the next word. That's how these models are trained. But what happens if we then let the model predict the next token when their input is suddenly 8,000 words or 16,000 words? That is something which is very challenging for transformers because it has never seen such a context in such a length in training data. So transformers in blue, they go riot and don't know what to expect. Of course, I have to say, if you were to train a huge transformer model, you would just give him flexible input sizes. So that is not a problem. But still, just the fact that if you feed a longer sequence to the transformer, this really gets problematic. Remember, it also gets very memory intensive. And the very last line here is the xLSTM. So train only 2,000 tokens, but then ran on much longer sequences. And basically, the performance stays the same, up to what we can measure so far. And that is very, very appealing, because suddenly we can generate build language models which then can produce much longer context, which then can read books much faster, which then can work on device because they're very memory efficient, since they work just their iterative way and they don't have to look at all the past. That is the first thing which keeps us very, very exciting. And the second thing is scaling plots. So here we've compared a bunch of models, state-of-the-art models, up to 1.3 billion parameters. Remember, I told you at the very beginning that the scaling laws are the only predictable laws in this huge black box optimization of deep learning. And these scaling laws are holding for xLSTM. So that means if we give xLSTM more parameters and more data, the model gets better, and it gets fundamentally better, and it gets still better than transformers. But we had 1.3 parameters. So this is not where it gets really serious. We have to go 1 or 2 steps further. We have to go to 7 billion, we have to go to 30 billion to really build these models which are as big as these models which are nowadays well used in Hugging Face compared with models from Meta and so on and so forth. That's actually what we're doing. But we see that these scaling laws are holding, and that keeps us super, super excited. So we know that there is something in this technology. We know that our technology is very, very good. We know that our technology beats the other models in this aspect, which are important for us. So the question is, where is this going? And as Albert said, we want to get international attention, so we don't want to stay in kindergarten, we want to play with the big boys. And that means we have to scale up our models. So far we trained at 1.3 billion, which is very, very huge. I think it's still one of the largest models trained in Europe, but that's definitely not enough if you want to make this hotspot worldwide. And we want to really, really hone in the advantages of xLSTM, which is that it works just very different as a transformer. And that gives an opportunity for downstream tasks. So for example, it can be very efficient on device application because it just doesn't need as much memory. It's very fast in producing things. It's very good at building semantic context, because, well, that's the way this model is constructed. It just builds this internal structure, so it will be very good at reasoning and semantic understanding. How good? Well, that needs to be seen, but we will we will make sure that we will use these advantages, and that's actually what we are now starting to ramp up. And then there's another development which is very interesting, which we were not expecting so much, but that's the problem if you have a very brilliant PhD student and whom you tell, well, Benedict, really focus on your task and on your thing, and don't look at other things, and then it tells you, well, I tried this xLSTM, you know, the code is public, and why should I not try it as well? And I put it into a computer vision model, and it works super well, and suddenly it has generated one of the best computer vision models. So then you of course have to deal with that, and so we were really excited to see that LSTM can see really well. How is this related to each other? And the thing is what I was telling you in the very beginning, the transformer are unified architectures. They work across all different modalities, all different tasks. And for example, you can think of in the lower left part as an image as something sequential. So you basically patch the image into these little squares, and you can see that as a sentence. And if you then tell in where this image, this token is, so to say, you can make an image to something which is a sentence and process with a transformer. And similarly, you can process it with an LSTM. You don't just raster over this image. And that works fantastically well. Of course, we have not tested it to an extent that we've optimized the architecture, that we have optimized its speed and so on and so forth. But just the fact that the plug and play of xLSTM into computer vision works so well is getting us pretty exciting, I have to say. And that brings me to the last part, because as Albert said at the beginning, we have two different branches at NXAI, and the second one is AI for simulation. That's actually where my heart lies, and that is really asking the question what is the language of science, and how we do, how we leverage these foundation models in science. And for me, these simulations are the backbone of our industry. They have something in common with language. They are time dependent, so they change over time. If you mathematically write it down, they are time dependent partial differential equations. And we use them everywhere in computation fluid dynamics, in modeling of different industrial processes, being materials, being mixing of materials, being multi-phase flows, being interaction of different fluids with boundaries, and so on and so forth. To silos on the right, and to rotating drums, and to granular material. And there's many of these simulations. And I'm very convinced, also coming from my time at Microsoft Research, that this is one of the big impacts of AI models. And because AI models can be scaled, AI models can be trained across different modalities, and these models will be used in a way we don't know yet 100%, but we know that this is going to come. So the question we are asking is now not how to fundamentally change simulations, but how to build so large models at that scale that they will really disrupt simulation, which in my opinion is going to happen in the next years. So the question is how we are going to do that. What does it take to build these models? And I would say it takes the ability to build large models. Very clear. Do we have that? Well, we have that in-house because we're training the largest language models in Europe, so we can use this infrastructure. It takes a lot of compute, obviously, both on generating data, storing data, leveraging data, and training big models. Do we have that? Well, hopefully yes. I would say we have that in-house. It takes knowledge of how to train across these different modalities and different data types. And this is where I think we shine, because we have that too. Why? I'm very convinced that we have that because I know how to build the best better models in the world, and I know how to build these simulations. 2 years ago, people didn't believe that we can build weather models, and now they go in production and going to replace numerical weather reports. And that's the same will happen to simulations. We've built a framework how to efficiently scale up the simulation. It's based on transformers. It's based on how to scale, so to say, simulations to a very efficient representation and move forward in time. Needless to say that when this works, we will get rid of the transformers and use an xLSTM here. And the third and the fourth point is domain knowledge. You cannot replace something which you don't know. And therefore we have hired a lot of domain experts where, I think this will become obvious in the next couple of months when we will publish in this domain as well. And this is basically the last slide of my talk. And I hope that I could evoke at least some interest in it.